ESD podcast number 2. It's taken 6 months to get here. The first one was back in January at the height of the beast from the east, polar vortex. But here we are 6 months later, back again. And it's my privilege to welcome an extremely exciting guest on what's going to be an extremely exciting topic, Dr. Andrew Rushby, who is a NASA alumni and also affiliated with the University of California in Irvine. Why don't you, so I had you down as an astrobiologist, I think in the, I did a quick slide to trail the podcast, and given the topics that we're going to get into and your kind of work, astrobiologist may be quite limiting, I think, but perhaps that was your first scientific incarnation. But why don't you kick off by giving us a few sentences about how would you classify your work and your kind of science bracket?
Sure. Well, firstly, thanks for having me on the show. It's a pleasure to be your second guest. I hope I can live up to the previous guest's very high standard. And thank you for the introduction. Yeah, I think astrobiologist is still a pretty good catch-all umbrella term. I was in a physics department recently, so I had the pleasure of calling myself an astrophysicist for a little while. But I think astrobiology actually provides quite a wide remit. There's astro in there, so you get some of the physics and the planetary science as well as the biology, which I would say I'm actually less of a biologist, and I certainly wouldn't want to classify myself as a biologist, more planetary science. But I think as maybe the discussion develops, the wide-ranging remit of this kind of research will become evident, and it's very difficult to then really put it into one single box. And I think that's one of the the defining characteristics of this kind of exoplanet habitability research, is its multidisciplinary nature.
I think I gave the title again when I trailed the podcast. I think I said searching for habitable worlds, and fundamentally, I suppose if you, well, it's a question for you as the presiding goal of the work that you've been involved in. I mean, is that kind of, if you were to have a Y above your desk, is it the search for habitable worlds, but also life, possible detection of life on those extra solar system worlds as well?
Well, the great thing about that is that they basically two sides of the same coin, right? We're going to be looking for habitable environments, I guess might be a better way to put it, not just on other extrasolar systems, but also potentially in our solar system and even on the Earth. Astrobiology does a lot of work actually here on the Earth, looking at, for example, analog environments that might represent something like a Mars or a very cold type environment. But it's also just about exploring the boundaries of life, how we understand life, what life is, and where it can thrive, where it can exist. And that's not limited necessarily to just extrasolar planets, but a lot of that work needs to be done here on Earth, both on the ground and up in the air occasionally, and from space as well.
And actually, before we go any further, I should welcome the listeners as well, and also that we'll probably have a wide range of listeners, some probably some fellow scientists, some customers of ESD, and also probably some friends and so forth. So I know you're a very experienced communicator and you run your own podcast, put a link in for that. So I guess for me as well, I'll try not to go into too much jargon and keep things broad but interesting at the same time. If I could be selfish for a minute, it's a fascinating area I absolutely love this stuff and the line of work that you're in. And of course, not to beat around the bush, when you've been affiliated and worked at a NASA laboratory, it's can be viewed as a dream to get to that level of employment in science is a phenomenal achievement. And I put you down as, or I think I referred to you as an alumni, NASA alumni, because I think it's maybe some people who aren't aware of how research happens. You often, if you have a specialism, you get affiliated to a program that needs a particular specialism and expertise. And that could either be at NASA or at a university, and then that program has a life cycle, and then you go on to something else. But why don't you? I mean, let's get to the NASA question. Could you explain? So you were at NASA Ames, which is Indeed. North California, or Is that right?
Yeah, San Francisco Bay Area, Mountain View. We shared a campus with Google.
Wow.
Nowhere near as nice as Google, but we're on the same campus anyway. And if it's okay with you, I might share my screen. I've got a little slide here
please.
that might help to explain a little bit more of this. So let me just maximize that and hope that you can still see everything okay.
Yep.
Okay, so I've just got a few little contact details there. If anyone watching would like to get in touch with me via email or check out anything on the web, my tweets and my podcast, which you've already mentioned. Thank you, Craig. That's exocast.org. We're the premier exoplanet podcast anyway, and we release a couple of episodes every month. But to get into the NASA side of things, I guess it's been a bit of a journey. I was born actually in Cape Town in South Africa, and after some high schooling out there, came to England, did my PhD at the University of East Anglia, where we met, of course, Craig. And then I was very fortunate to secure a fellowship at NASA's Ames Research Center, and you can see actually it made it into the EDP. If folks aren't familiar with Norwich Press, that's our local newspaper, and I was very proud to be featured, and there I am, looking very happy about the fact. So actually, when I was at NASA Ames, which, as you correctly said, is in Northern California, I was actually working for something called the NExSS for Exoplanet System Science, which is a nice little nested acronym, which also spells out NExSS. And this is a new kind of flavor of research coordination network, as it was known, that NASA was trialing at this time to try and bring together people from disparate centers in the US and actually abroad now as well, who are working on the general question of planetary habitability. So as I think our conversation will develop, we'll realize that there's a lot to be done here, and a lot of people from different disciplines and expertise that we really need to get into the fold. You can't really study this for just a single center, for example. So NExSS was kind of run out of Ames, and this is where I came into it.
So for people who, of course, everyone knows what NASA does, and in their mind they may think, well, they launch space vehicles and they explore inner and deep space, but beyond that. So astrobiology as a concept, is NASA Ames the home for astrobiology work in NASA? Would that be correct, as well as the engineering?
I guess that's fair. Yeah, I guess that would be fair to say. NASA Ames is probably primarily an aerospace and engineering center. I felt as a scientist there that we were maybe, the second rung in terms of like the priorities for the center. And that's fair. We have the world's biggest wind tunnel, have incredible amounts of like high technology, secret stuff going on there that me as a foreign national was never privy to. But certainly there is research going on there. And the Astrobiology Center used to be based there at Ames. And there has been some evolving processes over the last 5-10 years in which actually NExSS and these kind of more remote kind of research coordination networks actually replaced a lot of the geographical centers, for example. So I think NASA was trying to democratize this a little bit and have it less centralized and more spread out across a wider region, but just facilitated really by the folks at Ames. And that's what we were trying to do, set up that first initial contact, get the meetings together, get the funding so that individual researchers didn't have to pay for their own travel to get to places, put the meetings together, give some ideas, and then just see what happens, really, see how it would develop with that natural kind of impetus from the researchers themselves. And actually it was proved to be very successful. Well, depending on how you look at it, there were some folks who were quite upset that the Astrobiology Virtual Institute was being shut down here in 2019, but it was replaced by another 5 of these, or another 4 if you want to include NExSS. That makes 5 of these research coordination networks of the same model, with this kind of distributed network of researchers that are kind of brought together virtually and occasionally in person in a nice meeting somewhere. So I think Ames is still very much involved in leading that, but it's moved away from the kind of, we do this at one center. I mean, JPL does a huge amount of work. GISS, which is in New York, does so
JPL is well. Jet Propulsion Laboratory, and GISS is Goddard Institute for Space Sciences.
Actually, there's a couple of different centers on the East Coast, but yeah, there's Goddard Space Flight Center, and then there's the Goddard Institute for Space Sciences.
So you have at Ames you have the big engineering works. You mentioned the wind tunnel, and this is essentially building. I mean, I'm asking, is this building the hardware for landers on other planets, or is it for launch systems, or did they not tell you?
From what I was able to figure out, it's primarily re-entry systems. So that's the parachutes coming into planetary atmospheres, understanding drag, understanding how to slow craft down, basically, and survive that re-entry process. So I don't know if your listeners are familiar with, the Perseverance landing and the Mars Curiosity. Any of the MSLs would have landed with this pretty complicated multi-stage landing process, a lot of which was tested primarily at JPL, but also at Ames. And the parachute certainly can only be tested at Ames because we need that enormous wind tunnel. Because of the atmospheric pressure on Mars, it's a lot more difficult to slow something down. And when you have a car-sized rover coming in at escape velocity, you really need to figure out how to slow that down in phases. And that's what
Perseverance was a lander that landed recently, and if I remember seeing not footage but simulations or depictions of the landing, the lander had its own rock or propulsion system to slow it down. So it was almost like a SpaceX booster landing type concept, wasn't it? And then the cradle fired off to the distance, and that's so a lot of that engineering would have gone on at Ames as
exactly. I'm not too sure about exactly the proportion. I think a lot of it was split with JPL because they were the primary management for that. But Ames was also involved in not just the landing stuff, but also, for example, the Kepler Space Telescope, which I had the privilege to work on for some time. Actually, I was kind of part of the team as Kepler was being decommissioned. So Kepler was launched back in 2009, and without sounding like too much of a fanboy, it did revolutionize, without a doubt, exoplanet system science.
And this is a orbital telescope, is that right? So it's deployed in an Earth or is it a stationary orbit? And or you tell us a bit more about.
Yeah, it's at the Lagrange point 2, so it's an L2 orbit trailing the Earth, and it's actually out there at the moment in a stationary orbit at that distance. It is decommissioned currently, so it's not operational. It stopped working a couple of years ago. But the story of Kepler in itself is just a wonderful spacecraft. As I mentioned here, launched in 2009, so well over 10 years ago now, and it used a process called transit photometry, which I have a little animation of here. So basically, if you're looking at the star from a distance, from here on Earth, and you're looking at a distant star, of which Kepler was looking at 100,000 or so of these stars, it would look for basically just a slight dip in that brightness as a planet basically eclipsed that star, in between the spacecraft and the star, and you would see that slight decrease in brightness. And that's all it was doing, using a dozen or so CCDs, not much more powerful than a 2009 cellular phone camera.
So a CCD would be, what's a...
It's a capture device. So it's just capturing the photons basically that are coming onto the collection plates, and it's just determining if there is a dip in brightness. It's not giving any more information than this was this bright at one point and now it's this bright. So from that information, we can actually get a huge amount of data from about those planets themselves.
And so if a star exhibits this dip in luminosity, your first thought, or after checking for other things, your final thought, I guess, would be perhaps this is a planet in that system moving across the disk of that star, and therefore it's worthy of future investigation.
Yeah, very much the last thing. As you said, there's many more things that it's probably going to be before it is a planet, like an eclipsing binary, another star, some dust getting in the way, something in the atmosphere. There's I guess less so for Kepler, but there's always something in the way. And usually the last thing that we count for is a planet. That's basically how Kepler worked. And it was doing pretty well for about 4 years or so. It was collecting a huge amount of data until actually one of the reaction wheels failed. And the reaction wheel is a gyroscope that basically keeps the telescope pointing in the right direction. So it's spinning constantly and using that angular momentum to stabilize the spacecraft. And it has 3 of those. And unfortunately, one of them failed in 2013.
And was that the reason for the decommit? Did the telescope have a...
There was a fascinating, kind of human element to the story, in that the primary mission was still underway, and certainly the scientists didn't want to lose the spacecraft. So they worked with the private sector company. His name escapes me at the moment. I apologize. Might be Bell Aerospace. But there was an aerospace company based in Colorado that was basically kind of managing the spacecraft, and with the scientists and the technical managers at NASA Ames, of which I had nothing to do with, I should say, and they came up with this really ingenious way of basically using solar pressure to balance the spacecraft. So they didn't want to decommission it, and it changed from the Kepler space mission into the K2, which is the kind of second iteration of the mission. And it couldn't be as precise. It couldn't look at all of those stars with the same precision because of that reaction wheel failure. But it did allow for a new mission to take place in which we were actually using the natural motion of the stars in the sky to carry on these measurements at a slightly reduced accuracy, but you could still get a lot more information. So you might see like occasionally an exoplanet will be called Kepler 9, but then it became K2 118, and that will be the different mission types. They never gave up, and I thought that was
it's amazing.
A fascinating story.
I love the naming system. The names of candidate planets, they're really funny, like Kepler 164 b point blah blah blah. I always think it's funny. Do any of them get? I mean, when you're certain that you've discovered a planet, is a tendency, or is there an option there to give it a more usable name? And how
this has been a debate. This has been a big debate in exoplanet science for pretty much as soon as we discovered the first planets in 1995, 51 Peg. There was discussion. Should we start giving these the names that the solar system has?
Right.
And to be honest, it's pretty complicated. There's some political decisions here. What type of names do we give them? From which language do they come? From which mythology do they come? Are we imposing some bias there? And we're now up to 4,000 odd planets at the stage, I should say. I think I have a slide about that. Here we go. We are up to 4,100 confirmed planets at the moment. You can see a cumulative discovery rate here. And if you were coming up with 4,000 unique names, that would be incredibly difficult.
Numbers I guess numbers will do for now.
Yeah, and I mean, it does give a bit of info to the casual reader or listener. Kepler 9c might not make a lot of sense, but to the astrophysicist, there's quite a bit of info there. By the name Kepler, you know who's discovered it. That's the 9th discovery confirmed by Kepler. So Kepler 9 would be the star, and then it moves outwards from B, C, D, E, F, G, H in order of discovery, not necessarily in order of distance, which can be a little confusing, but in order of discovery. So there's never an A. A is generally the star, but then you have Kepler B would be the first planet discovered in that system. Kepler C would be the second planet discovered in that system. And then it gets a little confusing when, for example, you discover a planet that's actually quite close in, but discovered last. And you have Kepler H, for example, Kepler 119H, and that's really close to the star, but Kepler B is actually quite a long way away. So it can get a little confusing, but there's quite a bit of info in there as well.
You're saying around the 4,000 or looking at your slide here, 41,001 confirmed planets. And that confirmation is kind of like your 99.8% certain.
Well, 5 sigma. Ideally,
okay. Let's
or
break.
3 sigma.
Okay, so as an uncertainty measure, you're very certain that it's a planet,
and that's quite difficult to do because, as I mentioned, Kepler just uses this transit photometry technique, which is again illustrated here on the left hand side of the slide, and that's useful. It gives you 2 very useful bits of information: the radius of the planet and its period. So you can tell the radius by just how much light is being blocked out. It's just a disk, as you said, right? We're blocking the disk of the sun with another much smaller disk. And we can work out with a fraction, that's being obscured with the size of that radius of that disk. And also the time then that it takes to cross the planet, to cross the star's face will tell us the period from Kepler's laws. We can figure out, how fast it's moving will tell us how close it is. So those are 2 really, really useful bits of information. But really what we want me as a planetary science, I want the mass of that object, right? Knowing the radius it is useful, but it isn't as useful as it could be, because the radius, for example, of Jupiter is very, very large. Its mass is very, very large as well, but much of Jupiter is just a gassy ball, right? And we don't, certainly as a small planet scientist, I want to know how much of the atmosphere we're looking at, how much of the rocky surface of the planet are we looking at, and the radius doesn't give you that. It just gives you, whatever the radius of whatever the source is blocking that light. So you have to go to another method to get this confirmation. This is usually when a planet is considered confirmed, when it's detected by 2 of these techniques. So, for example, transit photometry is something that Kepler and now TESS is currently using up in which is also on orbit. But here on Earth, we can use something called Doppler spectroscopy to confirm that information, to discover planets too. And we like to do confirmations between these 2 techniques, and that can give us the mass, because the method that it uses is that it's measuring the wobble of that star in the sky. Basically, it's determining how if it's moving away or towards the Earth, very, very slightly. And if we can measure the slight amplitude of that wobble, we can infer from that there might be a planet in its orbit just pulling it slightly in one direction or the other. And as the planet pulls it away from us, it stretches the light from that star.
So when you're
longer wavelength,
and when you're trying to do that calculation, would you take into account that there may be other planets in the system that might be adding to that wobble?
Exactly. Yeah, and we can start pulling out multi-planet Doppler spectroscopy. It's difficult to do, and I've not worked on it personally, but I know folks who have, and they're very smart. And the methods that they use are very ingenious. There's a lot of dynamical simulations involved, but basically, yes, you can start pulling out multiple signals from this data, especially if you have the photometry as well, and just combining these two elements that give you that confirmation that says not only have we confirmed it with photometry, but we'd like to confirm it with spectroscopy too. And it's not always possible, because a lot of these things have to be rather serendipitous in how they line up. Firstly, if we're looking for photometry, the planet has to cross the star. And space is a three-dimensional, volume, and there is, some ecliptic plane and the galaxy, but there's no guarantee that the planet would be orbiting on the same plane as the Earth.
So if you happen to be looking down on the disk where everything rotates, the planets and the stars, of course, you might not see that. You wouldn't see the planet transiting the star disk from our position, or where Kepler's looking down from. That's a great point.
Yeah. So we have this uncertainty element called M sin I, which is basically the kind of assuming we're giving it a kind of a radius or a mass assuming a certain inclination that we can't yet prove unless we maybe have some Doppler spectroscopy. But then of course that has to be, just at the right distance as well for us to see it from Earth. So that not to be anything obscuring
it's fascinating. But if you get two strikes, the left and the right both check out, you're like, great, we've got something to work with here.
And unfortunately, there aren't that many planets that have both of these. Unfortunately, sometimes they just get confirmed by another photometer.
But the 4,000 that you referred to do have this double confirmation.
Not always from radial velocity as well. Some of them have just been confirmed by another mission, another radial velocity mission, another spectrometer, another transit photometer. So they're not always confirmed by different techniques, but they are confirmed by different mission.
And what
different telescope.
So if you can imagine Kepler pointing at a position or some part of the visible sky, and it's found, I think you found 41,000 planets.
So 4,100.
Sorry, beg your pardon. Yeah, 4,100. So what percentage of the sky has it sampled to get to that number? Just to kind of
very small. Yeah,
very small. I mean, that's
a very small. Actually, the primary Kepler mission, the one before the reaction wheel failure that I mentioned, was actually only studying one part of the sky. It was just constantly looking at one patch, slightly above the ecliptic. I can't remember the exact coordinates now, but it was just studying that single patch. It was actually chosen because it wasn't that bright. Turns out there's more than 100,000 stars in there that can be seen up at L2, so that's not a problem. But when it transitioned to the K2 phase, and we're actually using kind of just the natural motion of those stars in the sky relative to the spacecraft, it was moving along the ecliptic. And as it was doing so, it was sampling different parts of the sky. So it actually had quite a good coverage. But unlike TESS, which will actually have full sky coverage once it's done, scanning all of the northern hemisphere stars, scanning all of the southern hemisphere stars, to give a full sky survey. Kepler was not full sky. But this is actually a good point, Craig, because you mentioned there, kind of getting a kind of representative sample. And I think this is what a lot of folks maybe who aren't that involved in exoplanet science didn't appreciate necessarily about this mission. It was never really about finding Earth 2.0, which I hate. I shouldn't really even say that. But the next habitable planet was about getting statistics. It was about getting the big numbers and determining whether we can extract any patterns, extract any useful information from the distribution that we got. How many stars do you have to study before you can be sure that of all stars there are roughly 2 planets around one?
If you're devising techniques to find stars and to find exoplanets and then find out what they might be made of or what their characters are, you need a big sample size to develop those methods.
Exactly.
And then also to progress, I guess.
Yeah. I can talk about it a little later. I think I have a slide a little bit later on, but I think there's a kind of a statistics phase in exoplanet science, which we're currently still kind of in. And then there's going to be a characterization phase that will come next when we have the technology to pinpoint individual planetary systems or planets themselves that are interesting to follow up. But we need to identify them first, using something like TESS or Kepler, and get the big number statistics. If we look at a given star, what is the probability that star will have X number of planets, and what would their distribution of masses be, for example?
So I wonder if this is a good point for me to, I'm sure you might have got to this naturally with your slides, but I'm going to ask the question now, as I think it might take us somewhere interesting, that what do you do then when you've got a candidate planet and you can see it transiting the faraway star, and the light that's coming from that area is being, it's being modified somehow because the planet's going in front of the disk, and you examine then the character of all that light, and can you then begin to get a picture of whether the planet itself has an atmosphere?
Short answer, yes. Long answer, it's kind of complicated and only available in a very small number of planets that we have. Very hot. I'm not actually included here, but there is direct imaging of planets that is done, where we're basically just taking a picture of the sky. But those need to be incredibly young and incredibly hot and incredibly far away from their star. And we can get a little bit of info there, but what the technique you were describing there is called transmission spectroscopy. And if you imagine my transit photometry slide here, if instead we would be able to, as you said, collect or characterize the properties of the light that's coming through the planetary atmosphere, split it out from the star, and just determine the bit that's kind of being added, if you will, to the spectrum by the planet's atmosphere, then yes, we can start pulling out things like, how much, what's the distribution of gases in that planetary atmosphere? How thick is the atmosphere? Is any of it being lost to space?
The analogy I have in my mind, and it might be useful for people listening, but it might be wrong, so I'm looking to you to correct it, is so when you see old pictures of the space shuttle, and when it was pointing its camera through the atmospheric limb, or big, deep, it's kind of shaving through the atmosphere. And of course, it was predominantly red light because it was all being scattered on the other side. And so the kind of process that I'm imagining here is that if an exoplanet exists with an atmosphere and it goes across the front of a faraway star, could you detect that light modification, so that shift towards a particular part of the spectrum? And is that the concept? Is that a good analogy?
Yeah, that's exactly it. With the caveat being that this is only available in a very small number of cases at the moment, because of the difficulties in being able to separate out the star's light, which is 10 billion times greater than the planet's light, right? And it's getting that resolution at this angular distance. It's going to be maybe next generation or the generation after that telescopes before we can do this for terrestrial planets. But there is something called, there are a class of planets called hot Jupiters, which are very similar to Jupiter in our solar system, but just much closer to their star. And these allow for a little bit of transmission spectroscopy. My co-host on Exocast, Hannah Wakeford, who's a professor at Bristol, she does a lot of work on this and does some of the pioneering work on this, in fact, when she was at NASA, in terms of determining, and characterizing hot Jupiter atmospheres using transmission spectroscopy to determine, these incredible wind speeds and the fact that, their clouds are made of ruby and corundum and incredible heavy metals and just fantastic exotic worlds. But for me, as an astrobiologist, whilst they are very exotic and exciting, not that scientifically interesting. We're not going to find life there. Most likely.
So here's a question I'd like to throw out then. If you find a planet, or you take one of the 4,000, so what's the process then for what you do to begin to establish whether it's a habitable exoplanet? Let's get into that.
Well, I've mentioned here, I'll just go back a little bit. You can see there's about 400 or so of these Earth-sized-ish planets, up to about 25% greater Earth radius. So that's usually the first thing to look for. Is the planet roughly Earth-sized? That's not necessarily discounting larger planets. They could have moons, for example. But for right now, I think let's focus on the planetary size. And then the next thing is generally, you've probably heard of this, I guess. Maybe your listeners have heard of this as well, and that's the habitable zone. And this was, very big kind of mechanism for science communication when Kepler first started announcing planets. You might have heard, we found another planet in the habitable zone, and that is it's a scientific concept. It's an astronomical property of a star that describes a distance from a star where liquid water exists on the surface of that planet, but with the caveat in that we're assuming their planet has an atmosphere like the Earth. Water is a complex medium, right? It exists on the surface of our planet in 4 different states, in 4 different phases: gas, solid, and liquid. And the transitions between those phases are quite complicated. There's multiple different types of water, there's multiple different types of ice. So it's quite a complex medium. So we have to assume that the atmosphere of the planet that we're looking at has an atmosphere something like the Earth. And basically what this gives us is just another property about the star. This is something my PhD advisor, Mark Clare, who's now at St. Andrews, told me, is I don't think about it as about the planet. Think about it as about the star itself. This is just another property of the star that we can say, of a star this size and this bright and this old, there's a zone at this distance where if there was a planet like the Earth there, it could be habitable. And that's maybe the best way to look at this. And that's where usually the springboard of habitability started off.
So that reminds me of a question, and I'll ask it now if it's okay. What percentage of the star systems that you're aware of or NASA are looking at, what percentage of those have a sun-like star?
Actually, yeah, the sun-like or the G-type stars, they're not very common.
Why is it called G? Why is it called a G?
That's a good question. I don't know off the top of my head. It's the classification of the stars. But yes, for example, the primary type of star that is in our solar neighborhood is actually M-type stars, red dwarfs. And I can talk a little bit about them later. They're my favorite type of star. And actually in my previous postdoc at University of California, that was our primary research topic, was habitable planets around M-dwarf stars.
Because they're more common.
Yes, about 70% of the solar neighborhood are those. So the G-type stars, which are larger and brighter than the red dwarfs, are actually relatively rare. Maybe, don't quote me on this, but I think it's a number less than 10%, or maybe 10 to 12%. So the sun is kind of unusual in that respect. It's kind of common in many other ways, in that it's quite stable and it's not too flary. But it's kind of unusual in that it's quite large and bright. But the theory of the habitable zone is that if you find any star, regardless of whatever size or temperature it is, it should have a habitable zone, assuming those caveats we had about the atmosphere there. And you can see on this plot here, I've got, there's the classical habitable zone, as well as a hydrogen and CO2 extension, as well as a hydrogen as a methane extension. So the more we learn about planetary atmospheres and what gases can be stable in those atmospheres, the more kind of limiting the habitable zone became, because there were so many caveats tied up in it. And now there's actually a lot of different types of habitable zone emerging.
What are we seeing here so the x-axis is running along the bottom is stellar flux. So is that the amount of energy coming out of the star?
Yes, relative to what we get at the top of our atmosphere. So you can see the Earth there, right in the middle, at about about 1 effective
standardized to Earth.
Standardized to the Earth. Yes,
okay.
With lots of Earth bias in exoplanet science. Often things are considered an Earth masses, or effective stellar flux is normalized to the amount that we're getting at the top of the atmosphere here at Earth. So and you can see those different extensions and those different boundaries.
So if we move to the right along the x-axis and we get down to 0.5, so that's half of the stellar flux that we get here on Earth.
So round about what we get at Mars. As you can see, Mars is also illustrated there.
Great. And then you're saying if it's that weak, then the planet is likely to be not really habitable, or habitable by a certain definition. And likewise, if we get above an extra 50% of energy at the top of the atmosphere, things start to get cooking.
Exactly.
And you can...
Start to get cooking is a good way to put it, because it's a complicated situation. I can get onto this a little bit later, but my thesis work was looking at the kind of end of the habitable zone lifetime of a planet, that its habitable period. What happens when, all stars are the main sequence. That is, all stars that are converting, hydrogen and helium, into energy. Those stars get brighter as they age through the natural process of convecting. Actually, I guess the M-dwarf stars have full convection. They all have slightly different methods of converting that into heat and light, but they all get brighter as they age. Okay. The smaller stars get brighter much more slowly than the larger stars. The larger stars can have a main sequence lifetime of sometimes only hundreds of millions of years, whereas the smaller stars can be hundreds of billions of years. So there's quite a range, but they all increase in brightness over time. And what we wanted to ask was, okay, if they're increasing in brightness over time, at what point does it get too bright for the planets in their orbit, and what happens?
If you think of the habitable zone as a distance then from the star, and it might be, I don't know, several 100,000 miles to another several 100,000 miles, but as the star goes through its life cycle, that segment of space then moves out does it
Exactly.
to other, right? Okay,
I
and that's
I think
happening.
actually I have this here, so you can see there. You can have smaller stars tend to have longer main sequence lifetimes, and this does raise the question about long-term climate stability. What about those planets that are out of the habitable zone at the earliest part of that star's lifetime? Can they come into it at some point? Will Mars ever be
right? I was going to say
enough.
So this process is happening very, very slowly in our own solar system, and Earth obviously is in the in the habitable zone. But it's so that as our own sun burns hotter and hotter, the habitable zone will begin to slowly, very slowly, like go towards the outer planets.
Yeah, and we actually calculated this at around about 6.2 billion years from the formation of the Earth. So we have
say that again.
It's about 6.2 billion years from the formation of the Earth. So about 1.8 or so billion years from now.
That Earth will no longer be in the habitable zone.
Exactly. Yeah.
Okay.
When the sun will get too bright. What exactly will happen and how things will start to break down? That's a very interesting question. But round about that time, and actually, this is my first paper that was published in Astrobiology back in 2013, and it picked up quite a bit of interest actually, because I guess it was a slow news day, but people were like, "Oh, look, the end of the world! This guy's predicted the end of the world," and I ended up on Sky News at one point. I was on BBC World News. It got all a bit over the top.
You included a link in the notes, so I'll put this in the description as well. For this particular paper, I'll be sure if people want to follow that.
Yeah, I've tried to reference them all here at the bottom of my slides.
Great.
So we try to calculate these continuously habitable zones for a number of different stars, and we found that the Earth actually isn't that great. The Earth doesn't have that. Oh, sorry. Let me see if I've got any more data. No, I don't. The Earth actually doesn't have as long a habitable period as other planets could. As I mentioned, the G dwarf star that we orbit, being quite bright and hot, gives it about a 10 billion year lifetime, which sounds like a long time and is by any real measure. But when you have a small M dwarf star that could be on the main sequence for 100 billion years, 10 billion years seems pretty low, and that means that the the knock-on effect from that is that some planets could be in the habitable zone for 10, 15, 20, even 50 billion years. But I think that should sound alarm bells, and that did start sounding alarm bells for me, because I think there's a lot more to habitability than just the distance away from the star. And as you mentioned there, we always touched on it a little bit with Mars, in that, in theory, Mars will move into the habitable zone, or rather the habitable zone will move outwards to meet Mars's orbit at some point as the star gets brighter. But will Mars become habitable because of that?
Right, exactly. I mean, that's great. And it's just got me thinking, the ability, I mean, if you happen to have a planet with a particular atmosphere that is one way or the other more efficient at keeping energy or giving it off, then its ability to be habitable or in a habitable zone is obviously different.
Absolutely. Right. Yeah, exactly. Again, we're making this assumption about the habitable zone. Again, I don't want to knock it. It's a very useful technique, and it was developed or really advanced in a 1993 paper by a professor at Penn State, James Casting, and that is one of the highest cited papers in exoplanet science because of how seminal it was for helping us to determine where we should be looking for these planets, where our spacecraft should be looking.
Yeah, wow.
But the simulations that were done with a pretty basic one-dimensional climate model that I don't know if your listeners, certainly you and maybe some of your climates might be familiar with, but this is not a 3D GCM. This is a 1D radiative convective balance model with a simple Earth atmosphere that was assuming 200 parts per million CO2 and nothing else happening. And that was a snapshot of
break that down a bit. So for the benefit of the viewers, like a 1D, essentially a climate model is just an energy balance. It's just radiation in, radiation out. Therefore, what would the mean temperature be of the planet? And that planet, funnily enough, that planet could be Earth, or it could be an exoplanet. And it always confuses me. Some climate skeptics tend to get very excited, who are the very few remaining climate skeptics. Scientists often, when exoplanets are detected, they're happy to retweet the prospect that it could be habitable, quoting energy balance models that also prove that Earth is warming up because the atmosphere has changed. I always find that's quite a funny, sorry, just a little bit of a segue.
Well, it's oftentimes that people use, cherry pick data and use the things that seems to confirm what they found. And actually, as I mentioned, that 2013 paper, I ended up on Sky News and BBC World News, and I was actually confronted about, okay, well, you're saying the planet's going to be habitable for another 1.7 billion years. Why are we worrying with climate change? And even actually, it was mentioned in the Daily Mail that I was having an argument with people over at CRU, the climate research unit where you were based, and that was certainly not the case. We were using very different models. Like I said, that was using a one-dimensional carbonate silicate cycle model, which I could talk about a little bit later, but nowhere near the complexity to handle a 3D GCM, right? That would need that pulse of anthropogenic CO2.
At the other end of the spectrum of, I suppose, like planetary processes, if you want to just simulate what the planet, the mean temperature of the planet is, we've got these 1D, what we call one-dimensional energy balance models. And then, as Andrew said, at the other end, if you want to know what different parts of the planet, what the climate might be at different parts of the planet or in the oceans, then you need some method to circulate all the energy around. And there we have what we call three-dimensional circulation models, which are I mean, this is I don't want to short circuit where the discussion might go, but those types of models, the 3D models, often run for, well, firstly, numerical weather prediction, but then at longer timescales for predicting the future climate on Earth. But it's a fascinating thing to realize that these models can also be run in exo-planet mode. So to try and simulate, which you know way more about than me, and naturally, I don't want to shut down. Well, I don't know. Do you want to talk about that?
I can. I can actually talk about my model there. Let me see if I can jump into this. Actually, here we go. Landing climate models. So, talking a little bit about my, I guess, recent paper in which we tried to use going from that one-dimensional model, which is one-dimensional through the atmosphere. I should say that's the dimension that we're considering there. We're just, as Craig said, what energy is coming in, what energy is going out, what is the simple atmospheric gases in there that might be affecting that transmission. Whereas the 3D GCMs give you that chance to understand circulation, understand where the energy and how the energy is being moved around the planet. But modeling land in climate models, and this is just a general climate model overview here, is a relatively difficult thing to do. I think, Craig, you probably know more about that than I do.
So just to clarify, the question here is then, if you have a planet, how does the distribution of land and ocean then affect the properties of the
that's what we wanted to find out.
Yeah, so
that is exactly the question we wanted to find out. We're assuming so much of these one-dimensional models don't have any land, or don't have an ocean, or don't have the same split that we do. And if they do have the same split that we do, is that representative, right? And how would it change if all the land was at the equator? How would it change if all the land was at the pole?
But still with an ocean somewhere, so you can make up these.
Well, sometimes. Again, there's a lot of diversity in exoplanet climate modeling. I can only speak to CESM, which I'm going to touch on here, which is the Community Earth Systems model.
And that's one of the 3D circulation models.
Yes.
CESM.
Yeah, but I mean, even the Hadley model, which is used at Crew, I believe, and some of the other Met Office models. There's a French GCM that's often used. There's plenty of them in America that are used as well. Generally used, as you said, for numerical weather prediction, but we've also trying to adapt them now for exoplanet system science. And having a look at this particular figure here about what goes into understanding land surface modeling.
What have we got here?
Makes this very difficult. Well, this is just kind of an evolution here, but I just want to illustrate the things that are generally needed if you want to do land modeling properly. So, I mean, since the 70s, we started with those surface energy fluxes, those 1D models that we've already mentioned. But then the more stuff the modelers started adding, the better their models became, but the less applicable they came for exoplanet science. So I actually went to a meeting in Boulder, Colorado. There we go. I'm just combining all those words. And I had a chat with the climate modelers there at NCAR, which is the National Center for Atmospheric Research, and they were the ones who developed this model. And I said, your model is fantastic. I mean, look at all these things you've got in it now. Lakes and wetlands and urban heat islands, and it's just fantastic. But I don't want any of it. Take it all out, because I just want to look at exoplanets, and we can't assume that there's any of this stuff obviously going on in there. But what we did know is that the land is super, super important for understanding not just the energy, kind of balance, but also the differences that we might get around different stars. So when I moved to UCI, University of California at Irvine, my advisor there, Elmore Shields, was already working on some of this stuff. So she was very interested in those small stars, those M dwarfs, as I mentioned, and they're much cooler. And when you're cooler, any surface, any body that's emitting at a lower temperature gives off longer wavelength light, which is shifted into the red. Hence, they're called red dwarfs. And you can see the distribution of their kind of energy here in this top figure, which just shows the kind of normalized power density, if you will, like the percentage of flux in a certain wavelength band from 0 to just into the infrared, going through the visible. And you can see this here for different star types. You've got a red dwarf star, and then you've got kind of a G-type star like the sun, or the sun, in fact. And then I think you have a K and an F-type star as well, which is very much brighter. And you can see the brighter, hotter stars have a peak at a much lower wavelength, much bluer light. And the smaller red dwarf stars have a peak right out here at about 1 micron, which is much redder, much lower energy. But our question was, how would this then interact with the land, right? Once this light has passed through the atmosphere and is impacting the land, some of it's reflected away based on the properties of that surface, whether it's the ocean, whether it's trees, whether it's grass, whether it's tarmac. A certain proportion of that is reflected away. That's called albedo. And the amount of that's absorbed and the amount that's reflected is very important for understanding the planetary climate.
And that's it's often expressed as a fraction.
Exactly. As you can see it on the bottom figure down here.
Earth is 0.7 of it, so 70%.
So its albedo is 0.3.
0.3
because,
reflects 70%.
Exactly. It absorbs about 30% of the light that's incident on it.
So the process at the surface of the Earth is the Earth receives short, as you said, the sun-like star is emitting principally at the shorter wavelengths. And so the Earth's
right in the visible, actually, at about 0.6
right in the visible.
microns. Yeah.
And so the surface of the Earth, or what makes it through to the surface and absorbed by the Earth's surface, gets re-radiated at a longer wavelength. So for the intents and purposes of the Earth, it's converting shortwave into long wave.
Yeah. And we think that will be the same on any exoplanet, but how much of that is converted is a property not only of the material that's being impacted. For example, tarmac is going to absorb a lot more than ice will, but also the wavelength of the light coming in. Right. And this is what we realized, that it's not just about the property of the surface material, it's about the property of the light coming through from the star. And when most of your light is already shifted into the red around these cooler stars, that's going to have a very different impact on what's being reflected away, what's being absorbed and what's being reflected. And as you can see here, that peak at about 1 micron is coincidentally where there's a lot of peak in terms of the snow and this kind of mixture between this here in the albedo. So if you look at the albedo side of things, as you go up to 1 would be complete, absolute, everything is being reflected. 0 would be everything is being absorbed. And you can see it's kind of difficult to see with them all being black here. But you can see land is pretty much constant at around about 0.4. It does go up in the shorter wavelengths, but you can see ice and snow have a very powerful kind of wavelength dependent reflectivity, but they're reflecting a lot here in the kind of visible, which makes sense. When you go outside and it's snowy, you get blinded by the light because of all that reflectance. But as it goes further along, the reflectivity actually gets lower, and it's going to change when you're putting different light onto that snow. And this is actually something we found.
Here's a fun question. I hope a fun question to ask. But if our sun, if its emission profile looked more like the M class, the dwarf class that you've got on this,
that's AD Leo.
AD Leo. What would happen to Earth? Let's say it changed instantly. The sun adopted that emissions profile. Then everything's going to gradually cool off on planet Earth.
Actually, no. Actually, very interestingly, it's quite a few complicated things happen. So I'm going to skip a little bit.
Talk us through it.
But that's basically the question here. And I know this is not a great figure. I apologize. It's a little bit. There's a few too many lines and whatnot on it. But this basically answers that question: is if we were to put the Earth around a different type of star, how would its temperature change?
Right.
So you can imagine it reframing it around that way. But we found the M dwarf planets, because their reflectivity around snow and ice is very much different, they actually absorb a lot more energy from the star at those wavelengths. So snow and ice on an M dwarf planet is actually dark. It's actually darker than many of the land surfaces, which is bizarre for us to think about. And I should stress, it's not dark in the visible, it's dark to the star.
I was just going to, so visibly it's still white.
Of course, it's the same material,
course,
right?
Yeah.
But if we were somehow able to see into the infrared where this is kind of peaking, we would see a lot more absorption. They would look like dark surfaces. And when it's dark to the star, it's absorbing more light. And as it absorbs that light, it absorbs energy as well, which means that if you were to take a planet like the Earth and just put it around a red dwarf star at the same flux, you would immediately bump the temperature up quite a considerable amount, about 10 to 12 degrees, because of just the ability of that snow and ice to absorb more energy. Now, then that leads to the question, well, okay, if it's absorbing that more energy, it's probably going to warm the planet up a bit, which will mean that the snow and ice will then melt.
Right.
And interestingly, we found a negative feedback there, in which as you warm the planet up and that snow and ice does in fact melt, it reveals actually a much more reflective land surface than the snow was, which cools the planet and causes more snow and ice to form, which then warms the planet up. So you have this like nice little seesaw of like a stabilizing feedback.
Self-regulating kind of what
exactly.
I suppose homeostasis would have been the word given to it maybe in the 80s. And
that's what we called it.
It's still going around.
Although it's arguably not homeostatic in that it's not really regulated by life. That's not necessary for homeostasis, of course, but there's no life regulation in it. But it is a negative feedback, but only around the M dwarf stars. We would then surmise from that it's actually very difficult to go into a runaway glaciation. So this is something we think maybe happened on the Earth a billion years or so ago, was that there was actually a runaway glaciation called a snowball event, where the whole planet all the way down to the equator was covered in ice.
And is this just to, if there might be some listeners who know about climate processes, and of course, ice age and inter-ice ages are orbitally forced.
Primarily,
primarily orbitally forced by processes that are still with us. And we get interglacials, which we're in at the moment, and then a precession back to a glacial. But this concept of snowball Earth, that's something completely different.
Yeah, that could be caused, well, we're not really sure what caused it, right? And there have been a number of there's some potential evidence for them. It's still quite controversial, but there is at least a mechanism that makes sense, right? When the planet is cooled by some event, whether it be orbital, whether it be an impactor, whether it be a volcanic outgassing event, if there is some cooling and there is some growth of ice beyond a certain limit, let's say, I think it's about 30 degrees from the equator, on each side of the equator. Once the ice gets down to about that point, so much energy is being reflected away that the rest of the planet cools down enough for that ice to go all the way
there's no
to
stopping it. It's just a consequence of the new energetics of the planet. It's unstoppable.
Exactly. The albedo is then so high that there's not enough energy to reflect enough of that away. But we think around an M dwarf star, around those smaller stars, that wouldn't happen, because that energy would actually be released back into the atmosphere and would melt that ice, which would then cool the planet down a little bit.
So it's the nature of it's the wavelength of the host star can have all of these different impacts then, and what seems intuitive to us on Earth about a big ice or snow covered Earth gets colder doesn't hold in these other star systems because of the nature of the host star's emissions. That's
just amazing. One of the many things that we're interested in when it came to M dwarf planets. Right, as I mentioned, we were really focused on these at UCI in our group there. Wanted to understand a little bit more about M dwarf planet habitability, because the seesaw, which I have here, has gone back and forth on this. Actually, my advisor and someone you may know, Manoj Joshi, who I think you've worked with quite a bit at UEA, he did some of the early work on this. His 1997 paper was quite crucial to understanding, about M dwarf planets and what's going on with their circulation.
And Manoj Joshi was also at NASA Ames.
He was, yes. He was actually a postdoc there, a little bit before my time and before yours. But yes, we followed a relatively similar track. So Manoj was my thesis advisor as well, or my thesis examiner, I should say, on my Viva committee. And yeah, we stayed in contact and written a few papers together since. But he did some of the early work on this, and I must say it's not settled. My previous advisor, Elmore Shields at UCI, would like to say absolutely M dwarf planets are more habitable than G dwarf planets, but it's not quite settled yet. There are a lot of things that make them better for habitability, like the fact there's many of them. It seems like I'm not going to go into too much detail, but it seems like it's easier to form smaller planets, and it's easier to find them with our telescopes. Now, none of that says anything about habitability. That's more just a coincidence for us. But crucially, their stars are very long-lived, and they have effects like this, right? These interesting radiative and wavelength-dependent effects that we don't quite yet understand, like how much land, I can talk about that in a little bit, might make a difference, how much ice is going to make a difference. And then that's kind of counterbalanced by the fact that these planets are very, very close to their star. Because they're so much smaller than the sun, their habitable zones, which is of course set by the amount of flux that's coming from the star, by definition then has to be closer in. And they're so close, in fact, that they actually get tidally locked, like the moon is to the Earth. So one side is constantly facing the star.
I was just going to ask about, I thought this would come up at some point, and it's useful to to kind of spend a bit of time maybe explaining. So why don't you? So the Moon and Earth relationship is a good proxy for that. So could you kind of break it down a bit when you say tidally locked?
Sure. Well, it's basically, the Moon and the Earth is a good example. And actually, so is Venus. Venus rotates very, very slowly. It's not entirely tidally locked. But basically, tidal locking happens when a planet is, so close or at such a point in a star's gravity well that its angular momentum is basically nullified and it just stops rotating. Or it rotates at it has the same orbital period as it does.
So
rotational period as it does orbital period.
A useful analogy would be if if one day on Earth was 365 days.
Exactly. Yes.
Then London, for example, or any point on Earth would always be in perpetual daylight. So the Earth would be rotating 300 instead of 24 hours, 365 days, and therefore London's always pointing. And so is tidal locking this? So to get to that point in the planet's relationship with its star, is that common? Is it common for it to
absolutely
exist?
I mean, if you're within the tidal locking distance, then it's going to happen. It's just a matter of its dynamical timescale. How big the planet is, how much angular momentum it had at its formation will basically determine how long it takes for it to become tidally locked. Probably on the order of hundreds of thousands of years in most cases. Could
it happen to Earth or any of the well, you said Venus is tidally locked. Could it happen to Earth? It
absolutely could. And in fact, Earth's orbital and rotational period is slowing down. That's got something to do with the moon as well, the moon forming impact. But yeah, it is slowing down. And if we were certainly closer to the sun, it would be happening a little bit quicker. But it's a complicated question, I guess. But in the short term, yes, it's pretty common. Especially, in fact, we're assuming around any M dwarf that we're finding a habitable planet or quote unquote habitable planet, it's going to be tidally locked.
Wow.
Which then opens up a whole new range.
I mean, I'm just thinking as for climate modeling or even weather, if you have an atmosphere on those planets, and then what sort of process? What do you the mind just runs away with having half of the globe in getting heated, the other half obviously in darkness, and then the atmosphere is trying to balance the energy.
It's all about that atmosphere then.
And that takes you into some wacky kind of climates and weather systems.
And it's a great segue into my most recent paper. So well done, Craig. Good hosting. So I want to talk a little bit here about Trappist 1, which I think would probably have come up anyway. And I'd imagine some of your listeners might be familiar with this. This is kind of a kind of superstar system when it comes to terrestrial planets. It's a system of 7 small Earth-like planets around one of our closest stars, in fact, Trappist 1. And I've just got a quick artist rendition here, but also showing at the bottom here their sizes. You can think about it in density, I guess, but also the illumination. So that's the same measure as before, the incident flux.
And Trappist 1 is an M. It's an M. It is.
Star. Yes, it's actually a very, very small M. It's right on the border of not even being a star. It's that small, which again adds even more complications. So that distribution I showed of the AD Leo is about 30% the size of the sun. So it's much bigger than Trappist 1, which is only 8% the size of the sun. And again, a Trappist spectrum is very difficult to get. Well, some of it's modeled, some of it's from actual observations, but it's going to be even further shifted into the redder, longer wavelengths because of the fact that it's smaller and cooler. It's just basic thermodynamics. If the body is cooler, it's going to be emitting at a longer wavelength. So all of these planets, all 7 of them, are within the orbit of Venus. They're all squeezed right in there, but still stable because of the age of that system. We think they're dynamically stable. And you can see the habitable period, which is illustrated here on the bottom. Sorry, the habitable zone, I should say, which is this kind of shaded area on the figure at the bottom there. You can see the planets D, E, F, maybe G are possibly in this Trappist 1 habitable zone. So we thought, okay, this is interesting. There's a lot of work being done on Trappist, and all of the modeling that was being done with similar models to the ones we've discussed, right? The 3D GCM or 1D, but a 3D GCM, assuming an Earth-like distribution of land, assuming an Earth-like atmosphere and some ocean. So that's a crucial thing. There was an ocean included, and that ocean was generally a slab, which any climate modelers out there would know what that means. It's basically just not circulating, not moving heat around very well. It's the most simple version of an ocean you can have. So what we thought we would do, because we're quite interested in understanding basically land albedo, land reflectivity, because of that stuff I mentioned earlier about how the different stars, the reflectivity changes of the surface materials depending on what wavelengths coming from the star. We wanted to actually get rid of the ocean completely and just consider these as completely land-covered planets. So that was the topic of our paper. Imagine these are land planets now, that there's no water on them at all.
But with an atmosphere.
With an atmosphere like the Earth.
Okay.
So again, there's that caveat. They're tidally locked. They have an atmosphere like the Earth, but they have a number of these different land surface types. And it's completely equally distributed, again, across the planet's surface, not very realistic, but we thought as an extreme, most representative way of doing this, we just have an entire planet covered, for example, in iridisol, which is just an evolved soil, or an entire planet covered entirely in granite, which is just a very dark igneous rock, and see what the kind of the different radiative effects of that might be, taking out the whole ocean side of things. Now, I should say that there's been a lot of work done on TRAPPIST-1 systems and their oceans, and whether there are oceans or not. So, for example, Cayman Unterborn, who's at Arizona, I think, he's done a lot of great work on the potential for the TRAPPIST-1 systems to have an ocean. So I don't want to say that this is absolutely solved, but we wanted the comparison.
So you've decided to focus on land, and you said, right, exactly. Let's assume these planets don't have any ocean, but what's the probability that they do?
At this stage, somewhere between 0 and 100%.
That's a good answer. I think you could be right.
Yes, we think so. Well, it's going to be a little while for us to tell, but we think that water being as ubiquitous and common as it is, that there is going to be some water on these planets.
Right.
Now, where it's going to be, how it's going to be distributed, if it's going to be in the atmosphere, it's going to be the interior. That's actually a complicated question because there's some modeling work that we actually discussed this month on ExoCast, in which the planet's iron content seems to have a very important and powerful control on the thickness of the crust of the planet, and therefore how easy it is for water to get into the planet's interior and then back out.
I mean, I'll interject now with a question, and this is kind of getting back to this idea of eventually habiting Mars, if we want to, and
a land planet, of course.
Yeah, right. Great point. But also geologically dead, and there's obviously a problem that Earth is protected. Earth has a molten core which is rotating, and it's got iron in it or metal in it, and that gives us the magnetic field which protects our atmosphere from the solar wind, which is trying to strip it away. And one thing that surely comes up in the idea of terraforming Mars, and I'll ask you in a moment if you could comment on whether this makes any difference to your modeling of these planets. But for Mars, were you to somehow restart, I don't think this, I mean, this is just far out, going off on a segue here, but if you were able to reinstate Mars's molten core and it suddenly got its it's dynamo, right? A dynamo engine. And humans were pumping in an atmosphere, and it was we were saying, right, the magnetic field ought to protect the atmosphere that we're making, and therefore we can go and live there. The mass of the planet also needs to be of a sufficient. You need to have a big enough planet to have the gravitational field as well as the sun trying to strip the atmosphere away. Of course, if you don't have the gravitational field, the atmosphere will slowly fractionate away into space. That's
a good summary, and maybe I should have touched on my habitability discussion, because we kind of we approached it when we said, okay, let's imagine Mars becomes in the habitable zone, maybe a billion years from now. Does that make it habitable? And I would say no, because of that very fact. Like, unless we can restart, the planetary dynamo and add that planetary atmospheric protection, we're not going to preserve an atmosphere.
But in terms of the right? So that's one problem, but is the other problem its mass, and also these exoplanets' mass?
I would say so. I'd say actually it's more about the core mass fraction than the mass of the planet itself. So how much of the core of the planet is iron? How much of the mass of the planet is then silicate? And what's the ratio between the two? And if you have a planet something like the Earth at about 30% it seems that because we have so much of that iron and so much of it is kind of in the crust, it actually makes these very brittle thin crusts, which is actually very good for habitability because they move. And now that might seem like really bad for us and life when you have earthquakes and volcanoes and things that could be harmful to life. But it's fantastically important to get a lot of the gases that are kind of in the planetary interior back into the atmosphere to replenish the atmosphere that way, and add to that cycling process. And if there isn't enough mass to maintain that core, to keep the planet alive, basically, you're not going to get any of that stuff back into the atmosphere and none of it back out from the interior.
Great point. And so are any of those considerations, do they affect any of the modeling work? Do you kind of put that to one side?
Certainly in my carbonate silicate cycle and trying to understand the habitable period of the planet, what we did was we basically took the size of the planet and we assumed if it was something like the Earth, that based on its mass, it will have a certain amount of accretionary heat left over and a certain amount of radiogenic heat. So that's heat that's generated by the radionuclides that are uranium and potassium and all of that stuff, thorium, that are already kind of in the protoplanetary nebula and incorporated into the Earth. And they're what's generating also a lot of the heat from our planet on top of the accretionary heat.
So the accretionary heat would be when a planet like the Earth is formed, because it's hot and
it's
hot
basically what's left over from that formation.
And so that the interior of Earth, which is very hot and molten, is the residual accretionary heat. Is that right?
Some of it's accretionary. The vast majority is accretionary, and some of it's radiogenic. But the combination of those two things makes the interior heat budget, which drives that engine, drives that dynamo, and keeps the plates moving around. So for some of the habitable period stuff, where I said, these planets could be habitable for 10 billion years, what we assumed is let's look at that planet's mass and then just use a very simple scaling equation that says if it's bigger than the Earth, we assume it would have this much more accretionary heat and this much more radiogenic inventory from its protoplanetary disk, and therefore it will be able to stay alive, quote unquote, for this much longer. The bigger the planet, the bigger a planet is, the more heat it will have, which can actually be radiated away a little bit quicker, but it would have a larger radiogenic inventory, which will allow it to stay maybe warmer and more dynamic for a little bit longer. So I try to incorporate it in those long timescale billion-year simulations to understand how volcanism would change, because that's the primary driver of getting stuff back into the atmosphere. But for example, for these simulations where we were using a 3D GCM, these are kind of snapshots. They're like, done over a 30-year period of planetary simulations for 30 years. So understanding the decline in planetary heat isn't that important for this. We're assuming there is some, but it's not that it's it's not declining and driving changes in the planetary climate because of that. But it's something that we absolutely have to take into account. And without knowing the age of the planet or the age of the stellar system, and we're getting better at that thanks to Gaia spacecraft and ESA spacecraft, that's giving us really good measurements of stars, their size, their distances, their parallaxes, and to some degree their age as well. It's very difficult to determine if this is a young planet or an old planet and what that would mean for its geology and its geological evolution.
So do you want to kind of tell us where these experiments with the land surface led to?
Yes, these were experiments that we did using a 3D GCM, the Community Earth System model, which is primarily for understanding numerical weather predictions and land use change here on Earth. So very much pushing it to its limit. And to do that, we used a separate module. So this is a great system in that it's very modular, and we could add these different models and different modules to the model to help us to get a better understanding. And one of these was ExoCam. So we replaced the atmosphere module, the atmosphere box of the model, with something called ExoCam, which allowed us to do the exoplanet calculations for a red dwarf star around a tidally locked planet. Because this is such a great model, it's been developed for 20 years by hundreds of people. It's very difficult to pull out a lot of the Earth-centric stuff. Yep. So our collaborator Eric Wolf, who's at Boulder in Colorado, he developed ExoCam to try and do this, to give us the exoplanet stuff. So there we go. There's ExoCam there. That's just appeared. So this is these are what the distribution of temperatures look like on the planetary surface. So I've got a granite and a calcite system, so that's the top and the bottom row. And then for planet D, E, if it had if it was around the sun, and then planet F as well. So we've got 3 planets there, it can be a little confusing, as well as Trappist 1e modeled around the sun as kind of a control. Like, what would this look like if we were just modeling a land planet called Trappist E around the sun?
This is each panel here is a map. I should point out X-axis. So we've got east, west, north, south. So this is just like a land map of Earth and where it's.
Yeah, we've basically flattened the planet out into a 2-dimensional map, and then this is what the heat would look like. But because it's tightly locked.
Yellow is hot, blue's cold.
Yes, I should say it's in Kelvin as well. So apologies for not converting. But it's hot.
For example, it's tidally locked. So we've got one. So basically, the maybe I don't know, 90 east to 90 west.
Yes, exactly. That's the day side. So you can see the heat there,
okay.
And then the night side is basically the rest of it, which looks very much colder. So you have something called the eyeball, which is almost now a scientifically accepted term in exoplanet sciences. So we'll be like, okay, where's the eyeball? And you can see the eyeball of heat there, right under this what's known as substellar point. So that's the point where the sun is beating, or the star is beating down constantly.
Like midday.
Midday at the equator. But because these are tidally locked, it's always midday at the equator. So you can see that initial thing there. But there is some structure developing because there is rotation. As we said, the rotational length is the same as the orbital period. So these planets are going around there. I think the orbital period is like 30 days. It's a very small star. So they are rotating in a way relative to the rest of the sky, but they're not really rotating relative to the star. So you can see some structures are developing. There are some of these like kind of bleeding heat kind of fingers that are going out into the night side. But for the most part, there's a very, very hot area right underneath the substellar point, and a very cold area on the other side, the antistellar point. But the really interesting thing here we wanted to point out was the difference in temperatures based on the 2 land types. So these were like kind of our 2 extreme versions. So granite was by far the darkest and most absorptive, and then calcite was by far the brightest and least absorptive, most reflective.
So you're comparing D and F here. So far, sorry, no.
I'm comparing the top row and the bottom row. So you can see, for example, if we look at top left and bottom bottom left there, you can kind of see the very large temperature difference, something like 80 degrees Kelvin.
Granite and calcite, sorry, each row, okay.
But if you look at E, which has got this little symbol here, which actually means sun. So we're saying this is E if it was just put around the sun with a solar spectrum, right? This is another interesting comparison because it's getting the same amount of flux as the one to the left, where it's around Trappist 1, but the temperatures are very different. The reason for that being is that the sun, its spectral energy distribution is much shifted towards the shorter wavelengths, which makes it much more absorptive and reflective in different regions, which actually makes it cooler for the same amount of flux. So again, this is another one of those little things that adds maybe a little bit of benefit for habitability for these type of planets. Because of just the type of star. We're not even thinking about the type of land involved. Just the type of star. And it gets even a little bit more complicated. I won't go too much into this. It's maybe for the more technical viewers. Okay, so building off that kind of land temperature maps that we had there, we also tried to look at how this might work through the atmosphere to see where the circulation and the heat is being moved around, basically. So these are kind of complex plots. I apologize for that, but we've basically flattened down the planetary surface, and now we're looking at a slice through the atmosphere. So we're seeing the equator from north to south on the planet, and we're basically just looking at one slice of that to see basically where the heat is being moved around, and the yellow colors.
So we've got the height of the atmosphere from surface level at the bottom on the y-axis going up to the top of the atmosphere.
Exactly. Well, it's actually only the first
probably section of the atmosphere.
A few kilometers of the atmosphere, but that's where all the good stuff is going on. So I've cut off most of the top of the atmosphere. This is very much down at the surface. And it's going up into the atmosphere and across like north to south. So we're just seeing a snapshot. We're basically just seeing these atmospheric jets, which are these very strong yellow colors, which are just heat being moved along those kind of tropical kind of zones there that are just, that's how most of the heat is being moved around. If you look at the maps here, you can see them kind of sticking out, these kind of temperature surface derivations from the normal eyeball are just sticking out, and those jets are what's basically moving it around. So I guess in summary about, you know, kind of the land surface stuff, we found that the land surface material is very, very important. It can change the circulation of the planet's atmosphere and actually even start affecting its rotation itself.
Wow.
So I don't want to go too much into this, but we discovered that based basically on the ratio of the size of the features to the size of the planet and how quickly and how much energy they have, it could actually change the rotation of the whole planet itself and slow it down.
Amazing.
So knowing, again, we wanted to take from this that knowing what the surface of the material of the planet is going to be really, really important for getting any sort of idea about what the climate is. We can't just assume it's going to be silicate like the Earth. We probably have to explore a full range of materials that we might think could exist on those other planets.
So the idea of like a planet slowing down itself because of the particular land surface that it's got is, I mean, that's pretty mind-boggling.
Yeah, well, it's about the size of the structures, and basically I mean, as I mentioned, there's a dynamical timescale in which any kind of tidally locked planet will start to slow down. But we think the surface interactions with the atmosphere, the structures that form, the heat transfer will affect the rate at which that kind of angular momentum is lost, and that kind of dampening happens. Absolutely. But also just in a more general sense, it could add between 20 to 80 Kelvin to the average surface temperature, depending on what surface material you use. And this isn't even considering oceans yet. So
it's amazing. It's amazing. I remember
the difficulty of it all.
Yeah, I mean, if you were to speak to hardcore oceanographer, physical oceanographer, talk to them about the nuances of Earth's ocean circulation, the distribution of the land surface, and the idea that the ocean is trying to hemispherically circulate, but it can't because it gets impeded by Africa and South America, and so the transport of the energy on very slow timescales dictates aspects of Earth's climate, and it could all be radically different. For example, if ocean basins were freely connected around the globe, and it's phenomenal to think that the climate that we have here on Earth, which although it can be described very rudimentarily, we're talking about energy balances to working out the mean of the mean temperature of the planet, but then all these distribution of the land and the topography of the land, and
absolutely
you can give rise to all these different kind of permutations of what we might get on Earth.
That's what we're trying to figure out for exoplanets as well. As you said, like, let's imagine we have all of the land at the equator in one big island right underneath the substellar point. I mean, firstly, can an ocean be stable on a tidally locked planet? That is in itself a question. Secondly, what if there's no land? What if all the land is distributed in one place as opposed to the other? What if some different type of land with a different surface material is there? You know, what about the connectivity of those oceans? What about their salinity? How
I was going to ask. So salinity is a really funny feature on Earth, and it gives rise to density profiles in the ocean again that you wouldn't get if it was entirely freshwater.
Exactly.
So what would you assume about an exoplanet?
Well, again, not quite my area, but Manoj Joshi, who we've mentioned before already, and Jody Callum, who was a PhD student at UEA, they did some really cool early work on ocean circulation and salinity. And I can't, unfortunately to them, remember the immediate conclusions of that, but I do remember the implication being that salinity has a very powerful control for obviously determining how much heat can be moved around the planet. The more saline the water, the more heat it can carry, but the circulation can be affected in different ways as well. So salinity, I guess what anyone would assume at first principles would be, let's take an Earth level of salinity, I don't know, Atlantic basin salinity. But then of course, you know, we probably would have to explore a range of salinities to get a number of different boundaries that you could say. Under a high salinity, calculation, it would be this. Under a low salinity calculation, it might be that. But when we don't even know what type of land we're dealing with, we can't really make too many more implications about the composition of the ocean either. It's again, we just don't have enough info yet, and we're trying to, I guess. A summary of the last hour and a half is, how do we generalize the planetary system, right, to make it something that we can study and kind of support with our studies here on the Earth, but also that is adaptable and not Earth-centric enough that we can extend it to another planet that might be around a very different star.
It's amazing. I'm just looking at our notes, one of the things that we have in the notes, I know you put down the Drake equation and Fermi's paradox. And I guess what I'm segueing here to is we've spoken about the fantastic and the innovative work that's been doing on detecting planets, then working out possibly if they're habitable in the sense or in some criteria, but then getting on to whether they, or how you might think about detecting life on other planets. And so the Drake equation, could you give us a couple of sentences about that, and what you think the n number involved in the Drake equation is, if you want?
Well, if there's any hardcore physicists listening out there, the fact that we're calling it an equation, they might have some problem with that. It's more of, I'd like to think of it as a framework. So if anyone looks it up, and I don't have a slide for it right here, it's basically a number of kind of fractional estimates that we then add together to determine at the end of it how many spacefaring or intelligent civilizations might be extant in the galaxy at any given time. And it takes into account things like how many stars there are, how many stars form, planets like the Earth, how many planets like the Earth get to a stage where they can remain habitable for long enough, how many planets like the Earth then have life that emerges, and how much of that life becomes intelligent. So there's a lot of like kind of fractional estimates that we're putting in there, and they can range anywhere between, I don't know, put a number, 20,000 to none. And actually, we had an episode of Exocast. Again, I should stop flogging my podcast on yours. But we had an episode of Exocast where we went to a conference. I can't remember which one it was now. And we basically just asked a whole bunch of different people what their estimates might be, graduate students all the way up to professors, and got 3 orders of magnitude difference in terms of what people guessed.
There's a great clip. I'll put it in the description if I can find it. I think of Carl Sagan demonstrating the Drake equation, and I might be wrong here, but I think his n number was 1 billion. I mean,
that seems about right.
So, I mean that's phenomenal.
Carl was an optimist, right? And
he was an optimist.
The reason why he's one of my favorite scientists. If
he's
not
brilliant.
My favorite
he's great
scientist.
And when I saw you'd put it in the notes, I thought, oh, that's great. I'm sure Carl Sagan did this great visual, and I'll put it in. It's worth watching. It's maybe like 2 minutes, and he, as you state,
anything by Carl. If you're listening to this, go and watch anything you can find.
it's great, and he starts off with all the star systems, and then what fraction have planets, what fraction might be in the habitable zone, what fraction have been long enough to get to like a civilized point, and so forth. And I think he came up with 1 billion, which is it's absolutely outstanding. And kind of related to this, this is on the back of actually a Q&A panel that I watched of yours prior to this podcast, where I think it was either yourself or someone else on the panel was saying it would be far easier to detect a habitable world that's got life if the civilization had arrived at a point whereby they're modifying the planet or the atmosphere in such a way that becomes detectable.
Yeah, that's true. Actually, you're touching on a relatively novel concept called technosignatures. And actually, one of the last things that I worked on at NASA Ames, or as part of NExSS, I should say, was NASA's first ever inaugural technosignatures workshop, which was in itself a big deal. NASA is fundamentally a US government federal organization that tries to remain apolitical and uncontroversial when it can. So it's always been kind of moving the technosignatures, looking for advanced technologies, kind of to SETI, the SETI Institute, Search for Extraterrestrial Intelligence, which is a non-for-profit institute also run in Mountain View in California. But they kind of like demurred to SETI. Oh, SETI will do that. Now I think NASA are realizing that we can use a lot of the techniques and the telescopes that we have to start looking rigorously and scientifically for technosignatures, signs of advanced life. And as you said, the biggest one is going to be some sort of atmospheric, they're going to call it thermodynamic disequilibrium, but that basically means something's not right. Something is off in the atmosphere that shouldn't be. There's a gas there, or there's too much of a gas there, or there's just some feature that does not add up. And this could be a biosignature, it's just a sign of life, or it could be an advanced technosignature as well.
In terms of even exploration in our own solar system often picks methane as a signature for life.
It does.
And I couldn't tell you why, because I'm not a biochemist or anything, but I know a lot of the work on Mars is to try and find methane. Is that right? And
yeah,
why,
well,
why
methane's a pretty good gas for life. It seems to be one that's certainly made here by life on Earth. But the reason that it's always been considered a biosignature is actually, while we're talking about Carl Sagan, he actually had a paper in 1993 called The Pale Blue Dot, which was arguably the first ever biosignatures paper. And they used the Galileo spacecraft on one of its flybys en route to Jupiter, where they turned it around and they looked back at the Earth. And
it's an iconic photograph, isn't it? It's just a dot, and then he makes some very sharp kind of almost like, I won't say spiritual, but kind of,
I know the phrase. I know the passage you're thinking of.
It's brilliant. Again,
but that's actually from when the probe's almost at Jupiter. This is when it was leaving. They'd actually turned it back to see the disk of the Earth and determine, as we mentioned earlier, through atmospheric spectroscopy, i.e., what is being added or taken away from the sun's light by the Earth's atmosphere. Okay. They looked at the spectrum of the Earth's atmosphere to determine if they could find life. So obviously we know there's life on Earth, but what they wanted to do is assume that this was an exoplanet that they had this data from, and they wanted to figure out if they could find life on Earth. And the thing that they spotted was oxygen in the atmosphere, which oxygen being made by life on Earth, either trees or algae in the ocean, and methane, again, made by methanogens, which at this stage usually live in the guts of in the guts of cows, or under the ocean, or in some anoxic environments. But the key about oxygen and methane together is that methane should be destroyed by oxygen in a planetary atmosphere. After
naturally, it would just decompose into zero. You just completely
CO2 and water vapor, right? It would just a basic hydrocarbon that would just follow that in with sunlight anyway. Plus oxygen will go to CO2 and water vapor. So when you're finding both of those in the atmosphere, that's your smoking gun.
Wow!
Because they have to be being replenished. If you find oxygen, we now realize that I worked a lot on biosignatures while I was at NASA. We had a special edition in astrobiology, or 2 papers about it. But oxygen isn't the smoking gun it used to be, because we now know there are lots of abiotic or non-life ways of making oxygen, some of which can even just be from the action of water being evaporated in the atmosphere and the hydrogen being lost to space. So looking at oxygen itself used to be, oh wow, if we find oxygen, we can find life. And then it moved to, okay, if we find oxygen and methane, maybe we can find life. But as you mentioned there, we're finding methane on Mars, and we're realizing that, yes, it could be a biological signal, but it could also be a biotic signal from interactions with water and rocks, doing something called serpentinization. So understanding the source of the gas seems to be super, super important for really figuring out the biosignatures.
And to keep it closer to home as well, the other candidate in the solar system would be Europa, which is a moon of Jupiter, which either theoretically or has been proven that there's a liquid water ocean underneath an ice surface, and that's been proven that the
it's just the thickness and the covering of the ice shell that is a bit uncertain at the moment. But yes, there's absolutely water in there.
But then conditions then in this kind of subsurface ocean may be optimal.
And that's always the example I've given as to why the habitable zone doesn't always work, because Europa is a good 3 astronomical units, so 3 times the distance from the Earth to the Sun outside the habitable zone. It would be considered nowhere near habitable.
That's
but
interesting.
For me personally,
here it is as a candidate, as a good
I would
candidate
put it as probably the strongest candidate. Personally, again, that's coming from nothing but just my gut feeling, which is not good as a scientist, of course. But in terms of habitable environments, it's got the water, it's got probably relatively warm temperatures, at least at the bottom. It's got some geochemical inputs from the bottom, and it has also some oxidized products from just being in Jupiter's orbit. It's basically being ionized at the ice shell, and a lot of those products, which are very useful for life, are getting into the ocean that way. So you basically have all the ingredients you need for life, except for an atmosphere, and it's underneath an ice shell. So I think it's going to be very interesting to get out there and figure things out.
I mean, it's so is there anything to be said also for Venus, perhaps?
There is, and very timely.
Very timely. I know there was some press, maybe this time last year, where I think it was not towards the surface, but at some point in the atmospheric column, they had maybe found some other
phosphine. I believe.
Phosphine, right?
Yeah.
Okay.
So it was in about October last year. There was this phosphine discovery from here on Earth. It wasn't from an orbiter or anything. And the literature's gone back and forth on this. Again, we're talking about this on Exocast this month, because there has been 3 new Venus missions announced this week, 2 from NASA and 1 from ESA, from the European Space Agency. And they'll be going out to Venus at the end of this decade, probably 2028 to 2030. Not to look for phosphine. The phosphine discovery, because it was last year, was actually well after these missions were already in the development phase. But they will be looking for they will be characterizing the atmospheric profile, as you said, seeing what gases are there, and also trying to figure out what's going on the surface with its geology. And that's one of the big unknowns for Venus, is that it's so similar to the Earth, but it has very different surface. But it's hostile.
I find this an exciting example, because at the surface it's just inhospitable, it's hot, it's very high pressure, but as you get away from the surface with altitude, you encompass almost like a habitable zone of the atmospheric column.
And actually, Carl Sagan was quite interested in that.
It all comes back to him. And I remember there was this idea of aerostat colonization, which was the idea that you could find a point in the atmospheric column where the atmosphere was identical to 1 bar, so identical to Earth, and also by coincidence it might be a nice temperature, and so you could.
Exactly. You could absolutely find that. The problem being there are still sulfuric acid clouds everywhere, which is generally not good for life. But another benefit there that I only recently read about was the fact that because Venus's atmosphere is basically nitrogen and CO2, if you filled your aerostat vehicle for the settlement process with something like just the standard nitrogen oxygen mix that we have on Earth, it would be a lifting gas. It would act like helium, basically. Okay. So you could basically keep your aerostat vehicle suspended in the atmosphere a lot more easily on Venus.
Is this the altitude where the phosphines have turned up?
Well, the problem with the phosphine detection was that it wasn't how do I put this, altitudinally calibrated. It was a single point source.
To tell where
exactly.
Okay.
So like I said, it's gone back and forth, and actually there was some rather unprofessional developments in terms of how this discussion happened. Again, if anyone's interested, we talked about this on Exocast at the end of last year. But basically, one paper came out, said, look, we found phosphine. Another paper came out, said, no, you didn't. Another paper came out and said, yes, we think they did. Another paper came out from the original authors that said, yes, we still think we found it, but it's probably geographically distributed in ways that we can't detect very well, and we need a lander to figure it out.
Right.
So I'll be honest, I'm not sure where we are from January, but certainly up to January, it was back and forth a little bit. But the last thing I heard was that there could still be phosphine there. We still don't know exactly what its source is. And it could be a biosignature, it could be a sign of some life using phosphorus or some phosphorus related compound. And that phosphine would be some sort of a biological byproduct of that.
That's amazing. It's funny to think that on the one hand, there's all this amazing work going into looking for life outside the solar system, but there's still a lot to be discovered here.
Oh, absolutely.
And all the and different kind of almost like these kind of wacky worlds exist closer to home. So looking at for ocean life on Europa or phosphine-based life on
well, there is
Venus
one type of wacky world that we're missing, unfortunately. And I, again, if anyone listens to Exocast, will hear me go on about this quite a bit. But the planet class we don't have. I've already mentioned hot Jupiters, but they're quite unusual. But what's quite common, or seems to be quite common from the Kepler statistics anyway, is a super Earth or a mini Neptune. So that's a planet that's larger than the Earth, but smaller than their Neptune, which has about 17 times the mass of the Earth. And we don't have one of those in our solar system, and they would be so useful if we had one super Earth in the solar system to understand the transition from the terrestrial rocky planet to the gas giant or the ice giant. That transition is something that's really at the cutting edge at the moment of trying to understand.
Is that an expected transition for a planet? Sorry, do you mean like given one planet its transition from rocky?
No, what I meant was like
different classes.
Yeah, exactly. What happens to gas, basically? What happens to the atmosphere between the terrestrial and the ice giant or the gas giants? But one won't probably become the other. That was bad wording on my part. No. I mean, like the transition between the small planets to the large planets. There's some gap that we've identified called the radius gap, which is about 1.6 times the radius of the Earth to about 1.8 times the radius of the Earth. There seems to be some lack of planets in that region. Now that's from the thousands of data points we have from Kepler and what's coming from TESS as well. There just seems to be this bimodal distribution coming about, where you have planets smaller than that and planets larger than that, and then there's this gap in the middle. And I think a lot of the work that's going on at the moment is trying to understand the atmospheric processes that are controlling that gap. What is changing the radius? Basically, the atmosphere is going to be changing the radius, but what is controlling how the atmosphere clings to that planet and evolves over time? And if we had a super Earth type planet in our solar system, that would be that would help to solve a lot of those questions. And they seem to be quite common. That's the thing. They seem to be quite common around other stars, but not so much here in our solar system. So we're special in many ways, some of which are useful and some of which are not so useful.
So nicely put. It's let's kind of, I'm conscious of the time, and we should maybe think about wrapping up shortly.
Yeah, well done to the listeners if you've made it this long.
If the listeners will bear in mind, that's right. We've spoken. I mean, I could go on and on. I mean, it's not every day. You know, I'm lucky enough to chat to people in your line of work and with the employment history that you've had. And it's funny enough, I was thinking yesterday, we were lucky enough to have an in real life conversation in Norwich just a couple of weeks ago. And I wish
one of my first in quite a while. And
yeah, me too.
It was good to see.
It was brilliant to catch up and that conversation. I mean, we've covered most of the stuff I think we went through then. But it's funny, when I was driving home after that, I thought, I wish I'd recorded that. It was a phenomenal conversation.
It had that nice coffee shop ambience in the background as well. It would have maybe made for a good podcast.
It was great, and for the listeners' benefit, as I think you said right at the beginning, Andrew, that we're both UEA, kind of we're from the same stable, UEA, environmental sciences. So which is where we first met, I think, and so we have that common background. So that's principally how we know each other. But you kind of went into this really interesting branch of what I would call kind of like from a scientific perspective, it's almost like big Earth, holistic, all involved kind of viewpoint. And I can think of Andrew Watson, who people may know of, and before him, James Lovelock, who have this kind of planetary system way of thinking about things, which has led science in a really fascinating and exciting arena that you're lucky to be part of. Would you? This is kind of contentious, and so don't, feel free to answer or not answer if you want. But I spent a bit of time in the US when I was a bit younger and got taught actually in Colorado at Boulder, whereby I thought the thinking was probably more along those lines, whereas in Europe and the UK, I don't know if it's maybe to do with geographical size or maybe funding. I don't know, but I always thought I loved sitting in the classes in Boulder and speaking to American scientists. I don't know. Is it controversial to say that over in the States that kind of thinking is more encouraged, or there's funding there to kind of support that way of thinking about
it's an interesting question. I don't know if I guess I could draw on my own experiences alone, right, anecdotally. And my PhD advisor was Andrew Watson, of course.
I was going to clarify that. I thought it was
exactly. So I was fortunate to be influenced by this kind of system science kind of thinking anyway, initially about the Earth, and then he was very supportive when it came to my left field ideas. I'm like, oh, Andy, I just burst into his office and I was like, I come up with this new metric about habitable planet periods, and I think he actually at one point told me to take a deep breath because he couldn't understand anything I was saying because I was that excited about this. So I've got a huge amount of respect for Andy. He was doing some great work, primarily in oceanography, of course, where he's a Royal Society research professor, but also in multiple other things. And he kind of certainly inspired me to think a little bit more system science holistically about this. And in terms of the US question, that's a good point. I guess my graduate work was done in the UK with Andy Watson, so I had that kind of Earth systems feel to it. And then moving to NASA Ames, whilst it was an absolutely incredible experience. I was the most junior person there. There was no teaching necessarily that was done. As a postdoc, I was the bottom of the of the rung. We didn't have students. We had some summer students that would come through in the summer, obviously, but they were high school students that were like thinking about internships. So it was not like that teaching environment, which I did honestly miss. That's what I loved about going back to the University of California and working in our Elmore Shields group there at UCI, where we were actually building the group there. So the physics department, which you can see on the sides here, was very much more galactic cosmology based when I arrived. I think probably still is. They do a lot of dark matter stuff and neutrino experiments and stuff that's well out of my ken. But Aomwa and her group, and Paul Robertson, who's also there, is trying to build this exoplanet kind of group there. And I think the philosophy that we had was very closely aligned. I don't think that's a coincidence, because Aomwa Shields also worked with Manosh. It's a relatively small it's a relatively small world when it comes to exoplanet research, and most of it is absolutely done in the US. The funding is there. NASA and NExSS and these RCNs are much more of a have a lot more money and a lot more of it directed to this kind of work. But as I said, with the necessity of NExSS was the fact that there were these disparate groups working on this problem, coming at it from like slightly different points and never really speaking to each other. So I think it's a combination of the funding model in the US supporting this kind of stuff, but also the thinking about how we put it all together moving as well. And even at UEA, I was always considered to be like, a bit left field, a bit, jack of all trades. I'm throwing some oceans in here, some atmospheres in there.
When you're looking at these big, I think it's great. And I didn't want to do a disservice there to European research, because of course Andrew Watson was at UEA and now is still in the UK, so it can't be that be that restrictive.
And Bristol, Exeter, St Andrews, Edinburgh. I mean, there's lots of great work being done here. Absolutely. Tim
Lenton would be another scientist who springs to mind, who is in that kind of style of thinking. Absolutely. So I didn't, I'd like to highlight Charles Cockell actually as well at the University of Edinburgh. He was my thesis examiner, all those papers about habitability I mentioned were his. He's been kind of thinking about this and working in this field for many years, and is a pioneer in lots of it, including the philosophy of astrobiology, the why we do this as opposed to how. And he's also written a load of great philosophy papers about the potential of settlement on Mars and the ethics around that. So if anyone's interested in the kind of philosophy side of things, then check out Charles' work too. There are a couple of questions that we have on the, I think I put them on the sheet, which we can chat about. And again, if we want to skip over them, we can, and we'll try and get through it without torpedoing either of our professional standing assumptions.
I have to be careful sometimes, I'm on the fertile field.
You are, but you're you're right at the forefront, looking for alien worlds, looking for aliens. So the questions have to come
Craig, up. The way I would put it is, I'm looking for habitable environments, and I can always hide behind my my non-disclosure agreement that I signed at NASA as well. So.
Well, exactly, yeah. That's not to be argued with. But that said, answer however you want, or don't answer. But do you believe in intelligent aliens, and that we will somehow discover them, or they will discover us?
I like that you put the precursor of intelligent there, because I think people have asked me this before, and I feel very confident that there is most likely, I don't want to say simple, I don't want to say primitive, because those have connotations, but single-celled bacteria-like photosynthesizing organisms out there. It seems probabilistic, let's put it that way. It's the intelligence side of things that gets a little tricky. And there's nothing biologically precluding intelligence. We are examples of that it is possible for an intelligent observer species to emerge. I guess the big question is the coincidence of it. Us being coincident in a 13.7 billion year old universe.
In a time sense, or overlapping our civilization's longevity, overlapping with somebody
and that's one
else's.
of the features of the Drake equation, of course, is how long is this civilization around for. I mean, let's think about Rome, let's think about ancient Egypt, a couple of thousand years if you're lucky, a couple of hundred years at a push, and now our global civilizations may be a little bit different, right? We have more resiliency. Certainly if we can make it to another planet, we would have even more resiliency there, and another reason for us potentially to settle other worlds. But it's that coincidence of being extant at the same time as another species, and at the same technological level.
Right.
If you look back on the Earth 10,000 years ago, you wouldn't have seen any of our technological signatures that you might be able to see now. If you look back at the Earth 3 billion years ago, you wouldn't have seen oxygen, and you would have thought this planet isn't any good for life. So again, it's about capturing the time shot, the time scale and the snapshot of time, cool. And then also having us being able to see and communicate with them in any sort of meaningful way.
I guess that equally terrifying, I suppose, in one sense, is the idea that we're alone, exactly. But also that we're not alone, and there are civilized, or maybe even more civilized, possibly more civilized or advanced civilizations than us, but we will never be able to communicate with them. Exactly. But they're there. But they're there.
It's possible. Actually, I think one of the most interesting sessions I ever went to at a conference was at one of the NASA astrobiology conferences back in 2012. There was a panel in which some religious leaders and philosophers were invited in to discuss basically the implication of a finding of an intelligent life.
So was this saying, what should we do in the event that we find, or just
kind
how
of.
would
it was
this
like
change
how would your
religious
adherents,
narratives?
how would your followers, how would you anticipate an existential crisis might erupt from this? Because as a scientist, especially if you've been thinking about this for several decades now, like I have, it doesn't feel as controversial to me to say, no, I think that there could be life out there. But for many people who don't think about this all the time, for me, just banding out that statement can sound a little extreme. And I understand that. But that's why we thought we'd have the perspective from philosophy, from religious leaders.
Can I ask what their, if you're happy to,
sure.
what their kind of thoughts were?
Again, I'm going from memory. It was quite a few years ago, but I do remember the Catholic religious leader that was there saying that they didn't anticipate it would be a problem because that's just more people for them to convert, or more life for them to convert, to spread the good word of Jesus. And I was like, okay, that's one way of looking at it, certainly.
Okay.
The philosopher made a very good point in that there could be an existential crisis that's kind of galvanized in anyone on the planet when you realize that there's something out there that's an otherness to us, and that's the word he used, was this otherness, the inability to communicate, the inability to understand their motivations, the fact that they might want to eat us, which is a probabilistically non-zero chance, the fact that they might not be interested in communicating with us. Imagine that, right? Just finding intelligent life out there and then being completely oblivious or lacking the interest.
I was taking a look at the material that's on Voyager 1 and 2, and possibly on, would it be one of the Pioneer?
On Pioneer as well, the Pioneer plaque, yes.
The Pioneer plaque, and people will have seen this in various movies. It might even be in Independence Day, I think, or something where you get a snapshot of the plaque with our location on it.
Exactly.
I'd often think, is that I don't know, like who's going to pick this up? And I mean, it's very, very trusting of us to do that. And
it's optimistic, right? And again, Carl had a lot to do with those,
right?
The Voyager Golden Record and the Pioneer plaque.
So did he was on a panel that selected what material should go on all of those probes, wasn't he? And I think there's a collection of classical music, some day-to-day soundtrack,
world music as well, from
world music. That's right. Yeah,
they tried to be as representative as they could. They didn't have a great representation on those panels, but they tried to be as representative as they could in terms of cultural artifacts.
So I was thinking about this a couple of weeks ago again, about along that line of thought, and I think I mentioned to you in Norwich that that this is fairly topical, or in the last couple of years, the Oumuamua interstellar object that I think one Harvard astronomer theorized.
Avi
Loeb, thank you. Yeah. Theorized the only explanation because of its orbital character, or the way it's rotating and the way its albedo or its reflectivity change. He said it must be like a interstellar solar sail, but with rock and no meltable material, because there's no plume coming off it. I think that was his conjecture, was there was no visible plume, so therefore it's not like a typical composition of ice and rock. I think he was stating that. Is that right? And also
it's a pretty controversial series of statements. Actually, and Avi himself is an interesting character. He's clearly a brilliant scientist who hasn't really worked in exoplanet or astrobiology for very long. And I think he rubbed up quite a few people the wrong way when he came in with these very definitive statements about Oumuamua.
Oh, yeah.
And it culminated in a meeting at SETI, actually. Again, we mentioned SETI earlier, but Jill Tarter is one of the lead scientists there at SETI, and Jill's been working on stuff like this and leading the cause at NASA and elsewhere to try and get more funding for stuff like this for years. And the way that he attacked her when she asked for very reasonable questions about this really rubbed a lot of people up the wrong way, because whilst his conclusions are valid, they are not the only potential conclusions. And you make a good point there. He said, right, based on these orbital solutions, it seems like this is the most likely outcome. But instead of saying that, he said, right, this is the only option. It has to be this. It has to be an interstellar traveler. We did talk about this a little bit on Exocast when it first came out. We tried to follow the process of it along the way. And it seems like, yes, that is one option. It could be, there's a non-zero chance. It could be, an interstellar object from another advanced civilization. But there are orbital solutions that suggest it could be an oblong, asteroid or comet that's been misshapen over billions of years. So it's not as definitive, I think, as Avi would like to say. And I wonder if there were some political elements coming in there in terms of him being a relatively new but very senior scientist from Harvard, of course.
Right? He's at Harvard. So.
He's at the CFA, which is Center for Astronomy at Harvard, which does a lot of work in exoplanets anyway. And it's a big, very well-funded, very prestigious institute. And I wonder if maybe he felt he needed to be a little bit more, to drive this point home. Not necessarily to say we found intelligent life, but to get more funding, to get more publicity. I think it was coming from the right intentions, but it's like coming into a party late and just knocking over the punch bowl and saying that was the only solution.
Yeah,
it just seemed science is inherently a social activity, and there are politics in it, as much as we'd like to remove that, especially when it comes to funding. And I guess there was some political drivers behind that, but I don't want that to complicate the picture too much. It's still an interesting object.
It really is.
Know enough about it, and I think there's a lot more to be done.
Yeah, it's a fascinating, quite far out conclusion. Fascinating. I just thought it was funny that, if we're emitting all these radio signals and chucking out a few probes with some stuff on it, that someone might find it and then say, right, send the rock. Give them the rock.
Yes, this will answer all of their questions, of course.
Just send them the oblong-shaped rock, and
you'd hope it would be something
a
little bit more less controversial, right? Like a big flashing neon sign that says, "Hi everyone, we're here. This is where to find us," as opposed to a very esoteric, controversial oblong rock that's just really dark. Again, I think it comes down to the quality of evidence, right? For an extraordinary claim like that, you need extraordinary evidence to back it up, and I don't think that's there just yet. There's something interesting going on with Oumuamua, without a doubt, and it kind of brings to mind that the Planet 9 discussions as well, because Konstantin Batygin and others who had this idea that, and still are supporting it, that there could be another planet in our solar system as of yet undetected. It kind of has a little bit of that as well. Where
is there any evidence for that? Is there good evidence for that?
I'm not an expert in this, and I'd have to defer to their expertise and papers on it. But it's up for debate. The dynamical solutions that they use suggest that there could be some probability of there being another object there, but it could also be explained by other migration events. So again, we can't really tell. Yeah, it's one of those things that we think we should know better. It's our own solar system. We should know if there's another planet in our solar system, right? I guess it would be planet 8 now. But it's just out there a little bit.
I mean, this is all fascinating, Andrew, and you've been extremely generous with your time. But feel free to tell me a little bit about what are your plans for the future. Then you've summarised some of the areas that you've been that you've been active in historically and are still active in. And so do you still have an affiliation with University of California? Is that still ongoing, or what's the transition as you move from different projects to different projects? Tell us a little bit about that.
Well, actually, I've now unfortunately left UCI. I guess I still have some informal contacts there. I'm still staying in touch with a few of my students and making sure they're getting their papers done.
Great.
But I've moved on, and the reason for that is that's where diplomatic and bureaucratic issues intersect with science. So I was in America for 5 years, which was the maximum amount of time I could be on my visa. I was very fortunate that my time at NASA and my time at UCI crossed over so well, in that I think I left on Friday at NASA and I started work on Monday at UCI. So that worked out quite well. But since I left UCI, there has been a global pandemic underway. If you're listening to this in the future,
you were in the States for a big part of that.
I was in the States for the first half of it. Yeah.
Wow,
up until March this year, I was in the States.
Yeah.
And it was tricky.
Yeah, I bet.
I was very isolated there. If you want to get down into like the nitty gritties of being a scientist itself, especially a postdoc, right?
Exactly. I sympathize completely. And sometimes I think it's kind of difficult from people from outside looking into this kind of research arena. Firstly, the stuff you're doing is difficult. No one's done it before. It's research. You're the first person to try and devise these things. And you're often, although you have supervisors who are great and they're hands-on and they have a responsibility of care there, but it's still solitary. And it can, if things aren't going well, if you have problems with your research, doing the calculations and the results, it can be it's a very isolating and sometimes dark existence, and it's put a pandemic on top of that, especially if you're in a different country and you're worried about funding running out, which is universal to all researchers and not just in this area, and it's fact of life for everyone, I guess. But yeah, it can be difficult, but I
guess I was fortunate in that my advisors have always been very supportive, and Elmore was no different. I mean, this is a very unique and novel situation for us all. We didn't really know how it was developing, of course, but there was a good 10 months where I didn't see her at all, or the rest of my research group, and I was in my little apartment in Irvine, which was lovely enough, but friends and family are based here in the UK, and I had a little group in UCI, but certainly it was difficult, and as you said, throw a pandemic on top of the fact that we're always constantly looking for validation, whether it's from our peers through peer review, or whether it's from a funding body to say, look, I'm doing my best. Here's my work. I think that's relatively unique to research in that we don't. In other fields, you don't constantly have to justify your existence.
The analogy I always think is, if you're a good chef, you make the dinner, but then you don't have to go away and then write a journal article about what you did and then send it to other chefs who may say, well, I didn't
appreciate that. Exactly. But every year have to ask your restaurant manager to please extend your salary, or extend your payment for another year. It does seem a bit ridiculous when you step out of it. And when I'm telling my friends here in the UK, many of whom aren't in science, it does sound ridiculous coming out of my mouth that, I worked at NASA for 2 years, I worked at UCI, and now I'm currently, to be honest, unemployed right now. I'm in transition between different research and funding opportunities, and it moves very slowly. Academic research and funding moves very slowly. I'm basically waiting for fellowship opportunities to open, and then it's going to be another 3 months before they close and there can be a decision made. So
someone should do a podcast on and actually probably someone has, and I'm not just aware of it, but just on the lifestyle of people, the people out there who are doing phenomenal research on fixed term contracts, and over and above that, having to go through the peer review process, which can sometimes be a lottery. And I'm not critiquing. Science needs to be peer reviewed by brilliant scientists. So that's not a complaint. It's just the process.
There's improvements that can be made, without a doubt.
Yeah, I would agree. I think that's fair to say. But did you? I know you may well be in the process of devising new research questions that you may seek for funding. So you might not want to say too much on those areas, because obviously that's your personal aspirations. But is there anything you want to say about the big questions, given what you've done in the subject area so far?
Sure. We have touched on a lot of the work I've been doing. I think it would be an extension of that. It has to be, right? This is my area. So it'll be biosignatures most likely, and particularly how land is distributed and the effects of that land, as we touched on it earlier. What happens if you put it at the equator? What happens if you put it at the pole? And how does the circulation differ? So I think it will be still leveraging these 3D GCMs, these very powerful climate models, to try and understand a little bit more about what's going on when the land isn't, when you're don't just have a land planet when you have it distributed over the surface. Also, what that land looks like, you touched on it earlier, Craig, when you said topography, and that's something we haven't really mentioned yet, but that's certainly an area that I think is underexplored.
So where the mountain ranges are on the planet, and how does how does that,
and if you think about orogeny and how that even works, so mountain building on a planet that's larger than the Earth, you're going to have a higher surface gravity, which means that you'll have a lower angle of repose, which is going to change the weathering processes and all sorts, and that's barely been touched on yet. There's some early work
fascinating,
happening.
To bring it to an Earth analogy. The formation of storms is often depicted by where the major mountain ranges are. You get cyclogenesis in downstream sometimes of mountain ranges, and so the layout of where the Himalayas, the Alps, and so forth are can ultimately affect the local weather, but also the distribution of warmth around the planet that gives rise to.
And now imagine if that mountain range was 4 times higher on a much smaller planet, which could happen because of the lower gravity and the high angle of repose. So again, there's a lot still to be done, but I think as I mentioned, I kind of touched on it earlier, we're moving from this kind of statistics phase of exoplanet science to the characterization phase, and with the launch of James Webb, the James Webb Space Telescope later this year, hopefully, we'll start to approach the ability to get into planetary atmospheres.
So the James Webb platform, is it a Kepler replacement, or can it do other things?
It's a Hubble replacement, in fact.
A Hubble replacement, okay.
And even then it's much better than Hubble. So Hubble been up since the 90s, obviously, and it has a 2 odd meter mirror. James Webb has a 7 meter mirror, so it's much larger. Well, actually, let me double check that. It might not be 7, but it's larger. It's certainly larger. Hannah would be very angry at me right now, my other co-host, because I should know this, but it's certainly a much larger collecting area, and it will be doing not just exoplanet science. And I forget that, because whenever I'm talking about it, I'm like, I'm assuming this is just purely an exoplanet mission, but it'll be doing a lot of the things that Hubble did, extragalactic observations as well. But we're hoping to use some time that we get, and actually has been quite a lot of time allocated to exoplanet science as well. And we might start approaching the ability to understand the atmospheres of those planets. So the work that we can do here in the UK, especially with our climate modeling expertise, of which there is much of it, is getting into understanding what we might see when that starts happening. What if there's no land? What if there is land? What if the atmosphere looks different? What if the land is distributed differently?
So you could,
kind of prepare for the observations.
So I could imagine you could run a series of climate model experiments here with a set of hypothesized exoplanet configurations and put those on the shelf.
Absolutely.
And then when you start getting data from these new platforms, you say, well, does it match any of these pre-configured? And
just like we're doing with Venus to try and determine whether there's an abiotic source of that phosphine, we want to rule out any potential abiotic source of, say, methane or oxygen, or something that we might not be able to yet determine could be abiotic or could be biotic, so that when we do get a detection, when we can spectroscopically analyze that atmosphere, we can already be ruling out things like, there's also this particular band of deuterium, which means that it couldn't be from which it has to be from water loss, for example. So there's a number of things that we can do to get ready for those observations, and as we're doing so, understanding a lot more about general planetary systems. As I said, we didn't anticipate finding that the ice albedo effect might be reversed on much smaller planets around smaller stars.
It's amazing.
So that in itself was a big finding that we didn't anticipate, and we were just asking the question, what if? And there you go. I guess that's how science works. So I think that's what I'm going to hope to do. I'm going to hope to build a group here in the UK, maybe at UEA. I'm working with UEA and also in Edinburgh potentially, and anywhere else that wants to hire me if they're listening. So work together with a funding body to develop a group that can start doing this a little bit more, fit nicely into a group that's already doing this. Would be my goal.
It sounds awesome, Andrew, and I'm fingers crossed here.
Thanks, Greg.
That things will fall in place. I'm sure they will. Those sorts of questions are paramount. You're based down in beautiful Norwich at the moment, which is where
Norwich. It's nice to be back.
It's a beautiful. I love it down there. It's great. Although recently, as I said, maybe at the beginning, that I've moved up to Scotland now, but I'm close to Edinburgh, and so
another beautiful city.
It's hard to choose.
I'd say Edinburgh's right up there with some of my favorite cities in the world, certainly in the UK. So a split between Norwich and Edinburgh would be an ideal situation, I think.
It would be great. And if you're up here in the near future, or even at any point, be sure to give us a shout. We'll pick up the conversations. But it's, that's great. It's always great to hear about forward plans. I hope those come together, Andrew. And I'm
confident. And I've also, I must admit, I've been enjoying a little bit of time off. I have not actually had a break from school or work forever. I went straight from PhD to postdoc, and now I'm here. So I am getting a little anxious, of course. No one likes to be without a job, especially in a pandemic. But I'm feeling confident.
So sometimes those big ideas come together when you take a moment to, you're forced to take a breather. And it might be you go out hiking, or you're on a train, or if in Norwich,
the coasts in Norwich,
coast, or out on the Broads. You've got that big sky view, and
Absolutely.
you're like, this is where it all that creativity comes into play, and you latch on to aspirations, and I'm excited to see what happens, Andrew. And we'll keep in touch for sure. And I suppose just pulling things together, you've been, as I say, you've been really generous with your time. So I'll let you go now. You'll be pleased. But I hope you've enjoyed the conversation I have.
I absolutely have, Craig. Thanks very much for having me on the show.
You're absolutely welcome. And Exocast is your podcast. So thanks to all our listeners who are watching right now. Thanks for joining us. Hope you got something from this podcast, but be sure to check out Andrew's as well. So let's draw a line under it there. Thanks a lot, Andrew.
Okay, thanks, Craig.